So this is trigonometry, lesson 3.4, linear and angular speed. First of all, it'd be good for you to be aware of what both linear and angular speed are. You're already familiar with linear speed. Linear speed is the speed that your car goes down the highway. That's pretty much what linear speed is. So when we're talking about this point, P, it starts here and goes up here. How fast does it go from here to here? So it's going to travel a certain distance in feet or miles or yards or what. Let's just say miles in a certain amount of time. So 30 miles in an hour, 15 feet per second. So it's going to travel this length along a line in a certain amount of time. And the shorter amount of time it takes for this to travel, the faster it's going. So it may go 60 miles in an hour compared to 120 miles in an hour. So it's going a lot further. It's covering a lot more distance in the same amount of time as the speed goes up. Alright, so angular speed is the one that you haven't used much before. And angular speed is how fast this angle grows. So rather than this being how far this point P goes, this is how big this angle goes, how fast it grows. So maybe it grows 30 degrees per minute. So this line here is moving, this line here is moving away from this line at a certain speed. So this line may be going this fast, you know, and that would be how many degrees per minute. So let's say it got that far in a minute. Well, it just grew 100 and say 20 degrees in 1 minute. Or maybe it went from here to here in a minute. So that maybe that's 30 degrees in 1 minute. Because if you drew a line from here, you know, let's say that's 30 degrees. So that angular velocity would be this far in a minute. That would be 30 degrees in a minute. If it took an hour, it would be 30 degrees per hour. Okay, so that's what angular speed is, how fast that angle changes as P moves along the circle. So as P moves along here at a certain speed, this is going to grow at a certain speed, and that's what the angular velocity is, or the angular speed. Alright, so given that bit of information, let's talk about some formulas. So here's the formula for angular speed. That is actually a crappy American way of writing a Greek letter. That looks like that, which is a lowercase omega. The uppercase omega looks like this in Greek alphabet. And this one that looks like a W is the lowercase omega, which is one of the letters in the Greek alphabet. So, omega, which is angular velocity, equals theta over time, where theta is in radians. Okay, so if they give you degrees, you have to convert it to radians in order to use this formula. Alright, so let me get that drawing back on. Okay, so sorry my drawing is a little blurry, but theta is in radians, and that is this part right here, POB, this degree right here, given a certain amount of time. So it will go through a certain number of radians in a certain number of times. So like this one here, let's say that's a 45 degree angle, and you know that that in radians is pi over 4. So our answer would be pi over 4 per second. Or you might want to change that to a decimal. Divide pi, by 4 and get it in a decimal and say that's how many radians per second this line is traveling. Alright, so if you remember in section 3.2, we talked about this length right here. Remember that length is S. And we talked about that length S having a formula of s equals r times theta. Now, we're going to try to figure out linear speed then, a formula for linear speed. Linear speed is going to be velocity, which is speed, equals distance of s over time. So this is going to be what you're used to measuring, feet per second, miles per hour, that kind of thing, because s is a distance. Okay. And if that's true, and s equals this, we could say instead of s, we could put r times theta over t, couldn't we? And then we could write this as r times theta over t, because this and this are the same thing. Now look, I've got a theta over t, which is what I have over here. So I'm going to replace theta over t with omega. So velocity actually equals r, radius, times omega. And again, omega equals that. So we've got a couple different formulas here that we can use. So one of the things that's true is this formula right there relates linear and angular speeds. Because here's my linear speed, here's my angular speed, and I took my linear speed here and related it to my angular speed with this formula right there. So let's get started and looking at some of these. So in the middle of page 117, they're using as an example about somebody hitting a tennis ball with a tennis racket. So we have, let's say that this is the wrist, and this is the tennis racket, and this is the end. And what we're going to do here is we're going to find out how fast we can rotate through 90 degrees. Or, so this is 90 degrees, or pi over 2 radians. Same thing. Now let's say that the speed that you can swing this tennis racket through 90 degrees is 0.045 seconds. So that's how fast you can swing that tennis racket from here to here. If somebody would time it from here to here, it would take 0.045 seconds. So let's find out the angular speed. Let's find out how fast this line goes up to that 90 degrees. So we're going to use our omega, and that equals theta over time. Okay, this just tells you how fast you can do it. This will tell, or how many seconds it takes, the time. This will tell you what the distance is that this angle can travel in a certain amount of time. So we're going to put theta being pi over 2, 90 degrees, over 0.045 seconds. So that's how fast you'll travel through that. You can divide this all out and you'll end up getting a number close to 35 radians per second. So that's how many degrees you will go per second. So we weren't just figuring how fast you can do that. That doesn't really help us. It just says, yeah, 0.045, that's really fast. But this tells me that I can go through 35 radians in a second's time. Now, there are 2 radians in a full 360 degrees. So that means you can go around and around and around this thing 35 divided by 2 times per second. So 35 radians means about 17.5 circles around that per second. So that's not really usable, but it kind of gives you an idea of how fast this thing is going. So even though it's 35 radians per second, you're like, that doesn't tell me anything. Well, if going all the way around here is 2 radians, Well, if you go 2, 4, 6, 8, 10, 12, all the way to 35, you've gone around this thing 17 times in 1 second. And that's how fast that tennis racket is going from 0 to 90 degrees. So it's cruising along there pretty good. Now, if we want to find out how fast, if we want to find out linear velocity from here up to here, we can do that as well, because we can use our velocity equals r times w if we know what our radius is. Now this says, let's say that the radius, this distance here, is 2 feet. So now we have v equals 2 times, and we found my omega, we found my angular velocity, because velocity, linear velocity, is the radius times the angular velocity, and we just found the angular velocity to be 35. So that equals 70 feet per second, because they told us that we were dealing with seconds, and it also said that the tennis racket was 2 feet. So that's where we get feet per second. So if you take 70 feet per second, change it to miles per hour, you'll find out that that tennis serve from here up to, from here up to here, it covered 35 radians per second. But how fast is that? Well, that speed from here to here was 48 miles an hour. That's how fast you were able to swing that tennis racket.